Hello, November 14th. I'm with a little quadrant here, which is going to allow me to get the altitude of the sun above the horizon. This is a little homemade device of a protractor taped to a ruler at a right angle, a Starbucks straw on top of the ruler, through which the straight sun rays could pass and be projected onto something behind, which might cast a shadow in this manner, and a piece of dental floss with a bolt attached to it so that it hangs, when the ruler is horizontal to the earth, it hangs over the 0 point of the protractor. Hangs over the 0 point of the protractor. We can still that up a little bit. So horizontal to the earth, hanging over the 0 point, and then obviously as I tilt, that bolt keeps being drawn to the center of the earth at an angle perpendicular to the center of the earth, but the protractor angle changes. And so we want to get the altitude of the sun. It's a beautiful day to do it. There's not a cloud in the sky, and we've come to a nice spot here at Columbia that also has a lovely old, not that old, sundial, which we'll look at too. So we'll use the sundial to teach us about how the sun moves at a rate faster or slower than your watch over the course of the year. And right now we'll determine, based on the shadow of the sun on the sundial and our phone watch, whether the sun is ahead of our clock or behind it. And this is known as the equation of time. The equation of time. So those are our goals today: to get the altitude of the sun above the horizon with our homemade altitude determining device, quadrant, and to look at the equation of time. Hello again. We're going to try to find the shadow of the sun passing, the sun rays, I should say, passing through this straw and casting a shadow on this white pad. Let's see if we can get that. All right, so what we need to do is just hold this quadrant device up towards the sun so that it then, as you can see, casts a shadow on the paper. Casts a shadow on the paper, but I have to turn both the device, and you can see actually right there, I had it for a moment, the sun was passing through the straw right there. Now, unfortunately, my bolt is swinging a little bit. I'm going to try to tilt this a bit and slow the swinging down, okay, and come back. The sun is now going through the straw, and the bolt is passing over. It's swinging back and forth at about 23 degrees. So that would say that the sun is 23 degrees above the horizon at this moment. And what is this moment? Well, we need to know the time. And for that, we pause and return with the news that it is 2:08 p.m. on November 14th, 2020. And with that information, we can actually go to the computer and go to a lovely website called Time and Date and determine whether at this moment that is when the sun, where the sun actually is. It will tell us at 2:08 at what altitude the sun was. So that's our getting the altitude of the sun above the horizon. Now, we didn't get the horizon point, so for that we need to pause again, and I'll get the horizon angle, the azimuth. I don't know why I didn't say that to begin with. We need to get our azimuth, the number of degrees from north. Unfortunately, I didn't bring the right device for that, but I'll pause and do it with my camera and then tell you what I get. All right? All right. So I'm back, having gotten the azimuth with my phone and compass, and what we get is that the sun currently is 216 degrees from north. So that would be that I'm facing north in this direction and spinning around the horizon until I get to the sun. And when I do that, I get an azimuth of 217 degrees, 16 degrees, I should have said, I think I said before, from north. So what we need to note, and you could write these things down, is that we had an altitude of 23 degrees, we had a time of 2:08, and we had an azimuth of 216. And we can now go off and compare our data with data that we would get online, and then we could do one of our favorite things, and that is to calculate our percent error or percent deviation or percent difference from the accepted value. And we'd have to say that the accepted value is going to be what we find online, not necessarily that which I could get using my beautiful homemade quadrant, which again, all of you could make quite easily. It's not a difficult thing to make. You need a straw, you need a ruler, you need a protractor, you need a piece of dental floss and a bolt. And again, I like to use nylon reinforced tape. The rest I use masking tape. And in another time, I might have taken this apart and rebuilt it, but I didn't feel like I had the time. Oop, I gotta go get some paper that blew away. I'll be back. So I rescued my paper. So again, you hold your device horizontal to the ground so that the dental floss and bolt are passing over your protractor at 0. And then you simply point up at the object that you're looking for, in this case the sun, and you wait until you get that sunlight passing through, which I think we can see here, passing through your straw. That means because the straw is represents a relatively straight line for which the straight rays of the sun can pass. And if I double check again my angle from before, just to see, it should, if anything, well, you can tell me, would we predict that the angle should be more or less than the few minutes that have gone by? And I will tell you that I'm reading us now at a different value than I had before. A different value than I had before. That value slightly fill in the blank. Slightly fill in the blank. By the way, it's 2 in the afternoon, which of course means we're in standard time, which of course means that the sun has already passed the meridian. And if we remember, the meridian is the point at which the sun reaches its highest angle for any given day. So it should be that if I take a reading in the afternoon after the prime meridian has been passed, after solar noon, that the angle of the sun should be lower. And we could confirm that by checking the time and, once again, the azimuth. I did it. 2:16, 8 minutes later, 22 degrees above the horizon. And interestingly enough, I feel like my azimuth was actually a little lower this time at maybe 2:15, which you can determine whether or not I have made a mistake on the first one or the second one. If I'm getting a lower reading as the day has progressed, if I'm getting a lower reading as the day has progressed. So let's now look at the equation of time. We're now at the Columbia University sundial on the campus at Morningside Heights, and we want to see how this sundial and its time-telling apparatus compares with the time on our phone. Let's take a look at the sundial and see how it works. So the sun is captured by this parabolic arc. When the sun is rising in the eastern sky, the sun would strike this side, and the first time demarcation is a line where I'll point here at 7. You can't really see. 7, then 8, then 9, then 10, 11, and right in the middle, pointing at the meridian and south, is our noon, our solar noon. The brass rod on the top casts this shadow, which we can see, and I believe the leading edge of that shadow should be the time. Now, how do we read the lines on the sundial? Well, the major lines are the ones that go here, my finger 1, and then 2. We drop down, we see that's divided in 2. That would be 30 minutes. And then a 10-minute interval here, 10-minute interval there. So we have enough to give ourselves a fairly accurate reading from 10 minutes to 10 minutes between each hour. So we have 110, 120, 130, 140, 150, 2. And in this case, we are actually within the 2 and 3 o'clock hour. So you can see our shadow is fallen between the 2 and 3 o'clock hour, and it looks to me 2:41, sorry. So this is 2:30 here, this is 10 minutes later, and we're just past that. So 2:41 would be our time on the sundial. I'm gonna pause, check the time on my phone, and come back. I'm back, and what I've learned is that, in fact, the two don't match. The time on my phone is 2:29, and yet the time on the sundial is clearly past 2:30. It's clearly past 2:30, and it seems to me that it's 2:40, if not even 2:42 now. Then we have to go to another part of the sundial when this happens, when we have this disparity between clock time and sun time, because it turns out, based on the shape of the orbit of the Earth around the sun, that the Earth is not always moving in relation to the sun at an equal rate. And because it's not always moving around the sun at an equal rate, it doesn't always read time in exactly the same way from day to day to day. So what we look at is what's called an analemma, which is found always at the base of a good sundial, which gives you what's called the equation of time. And what this will tell you is how much the time is faster or slower in a given month. And if we look, we are in October, and if we read the top, the clock time slower than the sun time faster. Clock time slower is on the left, and sun time faster on the right. And what we see is that the clock time is definitely slower than sun time. I've read that wrong. So when the clock time is faster, it's on this side. This would be faster clock than the sun, and this going over here is slower. And we are slower. We're slower, according to me, 2:29 to 2:41, about by what? 2:29, 2:39, about 12 minutes, 11 minutes, is that right? 2:39, no, 13 minutes almost difference. And that looks like it could be about right for where we are, October to November, moving towards December. So we are somewhere, if this is November, we're somewhere in here, moving towards December, so about 13 minutes of difference. And how did I get that? I went up to the scale here, and maybe we're a little off the scale, not quite accurate, but not too far off. Because here's November, we're just about we're exactly halfway through, and that's, looks to me, about 13 minutes slower, our clock, than our sundial. So again, we got our reading. Our reading said it was 2:41. We went to our watch. It said it was 2:29, a 12-minute difference. We go to our analemma, and our analemma tells us that in November, and November would be this dot, December is this dot, right here. In this zone, we are definitely between 10 and 15 minutes slower than the sun. Now, occasionally, the sun and the clocks are exactly the same. And you can see here that there are moments like that. Here in January, here in March, April, and down here in December, which they didn't quite get on. In fact, the clock and time are usually the same on December 25th. The sun, did I say the clock and the time? I meant your watch and the sun. They are generally the same on December 25th. So this is a sundial and the equation of time, and with our little device over here sitting so placidly on a beautiful piece of pink granite, probably quarried from somewhere in Connecticut or Massachusetts for the lovely campus of Columbia. Here we have our device for getting the altitude of the sun above the horizon. And with that, I will say goodbye. We'll get just one more reading here from our sundial. So we'll move in, and again, we're now at 2, it looks to me, according to this line, we are approaching 2:30, 40, 2:50, not quite 2:50, so about, looks to me like about 2:46, maybe 2:47 I'm going to call it, even 2:48. I'm going to say that we're at 2:48. Now, if we're consistent, it should be on our watch about 12 minutes less. Let's check. Checking the watch, we got 2:35 and change. So I would say we're pretty accurate. We thought 2:47, 2:35. Again, a 12-minute might be actually have been 2:48, which would have been more like the 13-minute difference that I had at first thought. And we can see that time has already moved on, and we're now reaching for, we're at about 2:49. And when we get to that next line, we're going to be at 2:50. 2:50, and there we are. We're just about at 2:50 now. Again, how do we get that difference between your watch, your phone clock, and the sundial? We have to have the analemma, which is set in bronze here, and gives us, for again the month of November, gives us an accurate reading of an estimated reading between 10 and 15 minutes slower, our clock, which is, we confirmed when we looked at the sun versus the sundial's time versus our phone clock time. You'll note that you have to wait now until January and February for your watch to be moving faster than the sun.